All right, today we're going to talk about the binomial theorem. Now, the binomial theorem can be super beneficial for us in many ways. One of the biggest ways it allows us to expand very large binomials raised to high powers without actually using distribution over and over and over and over. And it's a lot quicker way. However, the process itself can be a little bit lengthy. So I ask you guys to be patient with this, take your time, and hopefully you will understand a little bit more about how this will work and things like that, and it'll be beneficial for you. So to start off, our vocab. A blank is a selection of items where order doesn't matter. So this would be going back and referring to that combinations and permutations lesson that we did. Now, the one that didn't matter, that would be referring to a combination. So that would be like taking X amount of things, or you have X amount of things where you're taking so many at a time, and it doesn't matter what order they're in. So this could be like drawing two cards from a deck, where let's say you take a King of Hearts and a Queen of Hearts. That would be the same as getting a Queen of Hearts and a King of Hearts. Those aren't two different things. For our second one, expand x plus 2 squared. So on this, we're going to need x plus 2 and x plus 2. So for this, I'm going to use FOIL or distribution. But by the end of the lesson, we won't have to have done that anymore if we can see the pattern that's going on. So that's going to be x squared plus 2x plus 2x. So that'll be 4x, and then plus 4 will be our final answer there. C, evaluate 5 factorial. Remember, factorials are multiplying, so we'll start at 5 and we're going to multiply by every number before that all the way down to 1. So this is going to be 5 times 4, which is 20, times 3, which is 60, times 2, which is 120, times 1, which will stay 120. So 5 factorial is 120. And then last, let's actually do a combination problem. So we have 6 total things taken 2 at a time. So just another notation of writing this, we can have C, and then we'd have 6 comma 2. Now, remember, this would be our formula for this. So we'd have 6 factorial over 6 minus 2 factorial times 2 factorial. So I'm not going to do 6 times 5 times 4 times 3 times 2 times 1. I'm going to actually do some simplifying first, so it makes it a little bit easier. That 6 minus 2 factorial will give me a 4 factorial on the bottom, and we want to close that. 4 factorial times 2 factorials on the bottom. Now that top, I'm going to write 6 times 5 times 4 factorial, because I know that those are just receding all the way down to 1, so those two can cancel out. 2 factorial is just 2 times 1, so 2. 6 times 5 is 30, divided by 2 will give us 15. That's a 0. So our answer for this, for a combination of 6 things taken 2 at a time, there's 15 different combinations there. Okay, so expanding binomials. So this would just be raised to a different number of powers, as you can see on the left-hand side. For this first piece, we know that anything raised to the 0 power is just 1. Now, all of these are written with both variables involved in every single term. I know that seems counterintuitive right now, but it forms a pattern that's very important for our lesson. So anything raised to the 0 power, 1, and then we'd have 0 A's and 0 B's. So it's just 1, right? Now that second one, A plus B to the first, we know anything raised to the power of 1 is just itself. So again, it's written a little goofy in here, but again, it's important for our lesson today. So we have 1 times A to the first and B to the 0, plus 1 times a to the 0 and b to the 1, which I know would simplify to just a plus b. But again, it's important to our lesson of how this is written out. We have a plus b squared, or to the second power, so that would expand as a squared, 1 times a squared and b to the 0, 2 times a to the first and b to the first, plus 1 times a to the 0 and b squared. So here we start to get kind of a pattern going on. I want you to notice how, first of all of our patterns, or all of our powers, are of 2. Now, first, they both start with a, then they get distributed evenly between a and b, and then they both go to b. So we have 2 with a, then we go to both of them, and then they both move over to b. Now, let's see what happens when we raise it to the third power. We have this 1 a to the third, so they're all with a, plus 3 a squared b to the first. So one of them moved over to b. Then we have this 3a to the first, b to the second. So you see another one went over to b, and then in the very end, all of them are with b. So they started with one of our terms, and then they all moved over to the other one by the time that we were done. Now, the coefficients, we'll talk about that right here. Now, the coefficients come from a pattern called Pascal's triangle. This is a very kind of famous pattern in math, and you can see it forms a triangle. Everything on the outside is composed of ones. So all the way down. So our pattern will kind of start in the third line where we have a plus b squared right here. So you look at the previous line, and again we have we have ones on the outsides, but then we add these two together and they give us that next term that's in the middle of it. And then from there, we can take 1 plus 2, and that'll give us a 3. And we can take 2 plus 1, and that'll give us a 3. And the outsides are still ones. And then the next piece, we have 1 plus 3, we get a 4. We get a 3 plus 3, we get a 6. We get a 3 plus 1, we get a 4. And then the outsides are still ones. So I'm going to do this raised to the 5th power. And we should be able to tell what the pattern is just based on how everything else is going. So our outside, we're going to have a 1. Then I'm going to have 1 plus 4, so we'll have a 5 in the middle of those two. 4 plus 6, we'll have a 10. 6 plus 4, we'll have a 10. 4 plus 1, we'll have a 5. And then a 1 on the outside. And that keeps on going. That's an infinite kind of pattern that we could just continue on, and it'll always work with expanding our binomials. Now there's another way that it could be shown, and we'll do that after this example. So we have a plus b to the 4th power. So let's look back, and that is this line right here. So I know that those are going to be my coefficients, 1, 4, 6, 4, and 1. Okay? So if I'm using Pascal's triangle like they want me to, I'm just going to write in those coefficients. So 1, 4, 6, 4, and 1. And all I have to do from this point is figure out what my powers would be. So I know that all of them start with my first term, or a in this case, where I'm going to have a to the 4th power, b to the 0 power, plus, and then they're just slowly going to shift over to that b term. So a to the 3rd, b to the 1st, plus a squared, b squared, plus a to the 1st, b to the 3rd, plus, and now we have none with our a's, and 4 with our b's. Let me shift that over a little bit so we can see everything with our b's. Okay, so if we wanted to simplify this, we can. We know that anything to a 0 power is just 1. So our very first term would just be 1 times a to the 4th, or a to the 4th, plus 4a cubed times b, plus 6a squared b squared, plus 4a b cubed plus b to the fourth. Okay, and I figured all of that out just by knowing that pattern from Pascal's triangle. And that's a lot faster than saying a plus b times a plus b times a plus b times a plus b, right? So rather than doing all of this and distributing to each of them, then coming up with an answer there, distributing again, coming up with an answer and distributing to the last binomial, we just have this whole pattern that kind of does it for us. So I hope you guys see the strength in using these patterns for Pascal's triangle and then for the binomial theorem essentially. So we can also think of all of these using combinations. So the first one would be a combination of 0 things where we take 0 at a time. So that's going to be 1. And I'll tell you right now, it's going to end up being the same coefficients that we get for Pascal's triangle. So we could write those in. All of them are going to be the same. So this can help you out, 1, figuring out different combinations, and 2, using the binomial theorem. So next, our actual binomial theorem. Like I said, I know this is kind of long, and this looks confusing. However, it's really not that bad. So it's essentially the same thing that we did in that pattern before. So this is just a plus b raised to any power. So we would take a combination of how many ever things are in that power, and then we would start it with 0 things and then take 1 at a time, take 2 at a time, 3 at a time, all the way up to the point where those 2 things are matching. And with our powers, they all start at a, and we don't have any with the first, all the way over to where those are all shifted over to b. Okay, so it's essentially the same type of thing that we just did in that last example, but it looks a little bit different. Down here, this is just a different notation. That's sigma notation. You'll use this more and more as the years go on, I suppose. So what this means is that we start at 0 and we go up to n. So our starting point is down there and our finishing point is at the very top, and we cycle through every one of those numbers until we're finished. So I'll write that out for our next example, and then we can I'll just kind of slowly do this. Okay, so what this would look like in sigma notation then, so we would start where r equals 0, because we're going to take 0 at a time and it's going to go up to 5. And then we're going to have take 5 things r at a time. So r is going to go from 0 up to 5. And then I'm going to have a, which will be x in this case, to the 5 minus r, and then our y term to the r. So if that didn't make sense, that's fine. I'll show you let's actually use that. So what this tells me is that 5 combination r, we start r at 0, so it's going to be 5 combination 0. So it's going to be 5 factorial over 5 minus 0 factorial to the 0 factorial. So that's going to end up being 1. Okay, so our first term is 1. So 1, and then we follow this again, 5 minus 0. So that's going to be x to the 5th, and then y will be our 0. Okay, plus, I would do my next term, 5 factorial, and now r is going to be 1 because I'm cycling up to 5. So that's going to be 5 minus 1, so this will be 4 factorial down here, and then 1 factorial. Now that's going to be those 4 times 3 times 2 times 1s on top and bottom will cancel out, so this will be equal to 5. So plus 5. Now we're going to have x to the 4th and y to the 1st. And I'll do this last one, and then you'll be able to see that from the top here, it's following that same pattern. So that's going to be 5 factorial over 3 factorial times 2 factorial. So the 3 times 2 times 1s will cancel out. So this top will be 5 times 4, which is 20 over 2. So that's going to give us 10. Okay? So plus 10. That'll be x to the third y squared. And then it's going to cycle through the rest of it. So plus 10 x squared y to the third. We're just using patterns here. Plus 5 x to the first, y to the fourth, and then plus 1 x to the 0. Y to the fifth. Didn't carry that one with it, that's all right. So we could simplify that down even further just by looking at our 0 powers and things like that. So it could be x to the fifth plus 5x to the fourth y, so on and so forth. So we'll do one more because it's a little bit trickier of an example, and then that'll be the end of it today, and we'll finish the lesson up the next time. So this is to the third power. So if this was in sigma notation, we would have r equals 0 again, and then that's going to go up to 3. We're going to have a 3 combination of r, and this will be 2r to the 3 minus r, and it's going to be a negative s to the r. Okay, so parentheses in this problem are going to be pretty important because, one, we have 2r, so we've only seen other pieces where it's just one term, and that negative is also going to play a part in this. So what this is going to look like, our coefficients, I'm just going to use Pascal's triangle so that we know we have 1, 3, 3, and 1. Now, let's just do those power pieces. So it's going to be 1 and then 2r to the third negative s to the 0 plus 3 2r squared negative s to the first plus 3 2r and then negative s squared, and then finishing up with plus 1 2r to the 0 and then negative s. These get so long. To the third. Okay, let me just make sure that those end up together. Yeah, we're fine. So let me simplify all these now, and then we'll be done. So 2r to the third will be 8r to the third. That'll be a 1, so times 1, so we have 8r to the third. This one will be 2r squared, so that's going to be 4r squared times 3 times negative s. So that's going to end up being 3 times 4 times negative 1 will be negative 12 r squared s. The next one, our r is 2r is to the first power, but our negative s is squared. So negative s squared is going to be positive s squared. So it's going to be 3 times 2 times 1. So that's going to be plus 6rs. And then at the very end, we have 2r to the 0 and then negative s to the third. So you can see here, because we had these different terms, because we had that 2r and we had a negative, it didn't really follow Pascal's triangle rule. I still use those numbers. However, throughout the entire thing, those kind of got changed up. So I hope that this was beneficial to you guys. If you need to go back and watch a couple of those examples, please do that and at least get those first couple of problems done on your lesson practice. Have a great day.